has to talk about Fourier transform and the communication, and it also its application on engineering side today. So, so the first thing I need to say is define the Fourier transform. So, what is Fourier transform? There are two meanings when we are talking about Fourier transform. The first way we talk about it is the frequency domain representation, and the second way is the mathematical operation that can be associating the frequency domain and the function of time. So what we're usually detecting is the frequency from all of the signals. But sometimes we need to transform them into sometimes we detect something as a function of time, but sometimes we need to transform to a function of frequency. So I think the first thing I need to talk about is how we define it in a mathematical way. So it was derived from Fourier series, which is kind of a math technique. And if you have learned quantum mechanics following that, so this is the eigenfunction which can be incorporated into the whole sum. So when you combine this two functions together, you can derive the following whole function for the Fourier transform. And what each integrand in this function means is that the g is just an imaginary number, and the omega 0 is the natural frequency, which I will mention later. It's a frequency used in a lot of fields, and this is the key term when we are applying these terms into the engineering side. So this is the final equation which we derived from the previous Fourier series. And so when we're talking about omega in this term, is like it's equal to the n times the omega naught. Omega naught is the natural frequency. And so I will just give you a simple example of how we used Fourier transform to transform from the time domain to the frequency domain. So this is a spectrum or a signal from when you're saying a hello. So it's so the machine detects the sound of the hello, and then this is how it's represented in the waveform. But in the real form, you couldn't read something because the amplitude is so unstable. So if you want to really get analyze of something, you need to get a peak and take the integration of that peak. So you know the area of that peak, and use the area peak of knowing how large the signal or the amplitude of your loudness. So when you transform to from the original waveform, so from here to here, it went to the Fourier transform, and then you transform some waveform like sine waves to several peaks, and then you can analyze this peak to get what you want. And also, there's also some other cases when the noise was added, because in real life, when you're detecting some sounds, there will be some noise, probably coming from the environment. There are several sources of noise, probably I think generally will be 5. So the noise may come from the thermal condition you are detecting with, and also the noise may come from the environment, and also there are several different types of noises when you apply the recording of sound in numerous areas. So when you are measure the waves, when you add the sound, the waveform will be becoming even more complex. So after you have already a very complex waveform, after it's transformed to the Fourier transform, you can easily find out what the noises are, and also the little huge peaks which do not normally occur in the regular peaks. So comparing to these two curves, you are really kind of easy to recognize what is the noises and what is the real peaks of your sound. But if you're looking at this, you couldn't really distinguish what are the noises and what are the real sounds. So it's a really good way to distinguish things you want to get and the things you would not like to get. And so later on, I will just talk through a series of the applications by the Fourier transform. So the first and the most amazing part it gives us is its ability to analyze the differential equation, and that's a kind of a really common phenomenon that happens in the mathematical area. So if I can give you an example, that would be kind of the Gaussian transform. So first we have a kind of equation or a problem we want to solve, but the equation is really hard to integrate, or it's really complex to solve. What we can do is transfer the original function into another function that can be expressed in the other way, and by the Fourier transform. So here, this function will be much easier than this function. So probably after this transform, this could be transformed into a very simple algebra. And you solve in this area by solving this really easy problem, and then you got a solution, and then you transfer the solution back into the complex field, which your original purpose for getting the solution of the original problem. So it can be kind of carry your stuff into another field and then solve that problem and come back and get your final answer. So later on, I'll just give you several examples. So this is the functions, which looks really weird and really complex. Then after the Fourier transform, it just transform into a kind of a simpler form. And that's the magical power for the Fourier transform in the mathematical area. And also, it has a lot of application in the chemistry side. So one of its application is that the Fourier transform makes spectroscopy. So in the spectroscopy, we also need kind of transfer the signals into the peaks, because we need to know the frequency rather than the signals, because when we're detecting something, they are kind of oscillating in a kind of a weird order, and our machine can only detect the amplitude is oscillate, but we couldn't detect the frequency. So here we need the Fourier transform to do that. So this is a picture of the examples of the cyclotron resonance machine. So what it actually do is to put some molecules here, and then by the features of the electrons, it can be excited, and the electron can be excited and kind of oscillate in a way. So the machine can record the amplitude of the oscillation of the electron, and then it can be recorded in this form. And the form is transformed into the peaks, which we can integrate the area of the peaks. So we know in which time or in which state the electron has oscillated. So comparing with the standard, we're able to know what kind of a molecule it is. So for example, if we have a molecule with a OH group, and so and probably several, maybe we have 3 OH groups, and if you can compare with the standard, for example, with only one OH group, and like the peak will be like this. And the straight edge group was this is called polarity. So it's kind of determining how much electron is contained in that functional group. So straight edge group people like look like this. So if we already know the peaks of this, we can identify what kind of a molecule is in a specific chemical structure. And that's how we use the mass spectroscopy. And because the mass spectroscopy is able to determine the mass to charge ratio, which is the ratio between the mass of the molecule and the charge of that molecule. So in this way, we can use Fourier Transform spectroscopy to determine the specific kind of a chemical compound in a variety of field. So in this way, we're probably, for example, we're able to know like how much blood cells in our body or in a particular part. So we can analyze it into the medical factory, like give the report to the hospital so they can know the condition of their patients. And this is also an internal theory of how we use the Fourier Transform mass spectroscopy. So they create an internal electric field, a magnetic field, and the signals is reported to the computer, and also the ions is input and they can calculate the amount of ions of a particular species, and this is the way how they analyze the structures of a particular molecule. And also, the Fourier Transform have a great application on the MRI and MR. So they are basically the same thing. The MRI is just showing the result and the image of the NMR. So the NMR is nuclear magnetic resonance, which use the resonance of the molecules and also the nucleus in the molecules to identify identify the compound and the signals of a particular molecule. So so I draw a little graph here. So this is basically a wire, and I'm just showing a simple version of how NMR works. So it's a little wire, and you put a magnetic field into this. So if there is a molecule, and this will have a nuclei. So this will have a nuclei and a lot of the electrons surrounding it. So if you apply a magnetic field, there will be kind of a moment, kind of giving the nucleus a force, because it's kind of because there's a charge on the nucleus and a negative charge on the electrons. So it will give a torque or a force on that side. So when it's using the force and the torque rotating the moment of the charges, it will give you an angle, and what we can analyze is the angle of that charge. So if we analyze the angles in particular coordinates, we're able to measure how the moment of the charges has rotated. And after we know that information, we can compare with other samples, and then knowing what the structures and the molecules of that. And that's how NMR works. And also, the last thing is about its application in the signal processing. What it actually do is there will be always a delay when you're detecting some signals. So, so what the Fourier Transform do is to kind of cut the bridge of these two of the signals. So it can help you to get the signal as soon as possible. And this is the function how how it goes, and it's pretty similar to our original Fourier transform function. Sorry, and that's all.
Any questions for Chengtong? Quick